welcome to the lecture. Today we are going to be talking about another type of popular framework in neural networks known as convolutional neural networks, and they have proven to be very effective and successful, especially in computer vision domain and in image processing domain. So if you have problems where image is your input, then this class of networks have basically been very effective in solving very multiple problems which are interesting. So let's talk about that, and today's focus is essentially on convolutional neural networks and their applications in various domains that we'll see around. Okay, so let's get started with this. Essentially the deep neural networks and the idea that we have multiple hidden layers within the input and output layer, and that allows us the ability to learn a very complex model which can do phenomenal with respect to doing input and output mapping and learning a model that can lead to very good models, right? So essentially deep neural networks or DNNs are good to learn a model. Okay, now one of the challenges with deep neural networks is they typically have multiple hidden layers, and they also have multiple levels of neurons, multiple neurons in a given layer, and due to that there are typically a large number of parameters or the weights that require us to tune them. Okay, so the question is, do we really need this fully connected model where everything is connected to everything? Okay, and do we need all the edges? And more specifically, can we be more creative in sharing those edges, at least in some specific applications, right? Maybe it is not possible to do remove these edges in all the application, but can we do something in specific application? And it turns out that convolutional neural networks are essentially a class of techniques which allows us to replace some of these edges specifically for image processing tasks that we have. So for that specific application of image processing, we can have a convolutional neural network which has like a slightly different framework, slightly different computational pipeline that allows us to simplify the model, so the number of parameters that we need to learn will be smaller than the classical deep neural networks that we have. Okay, and that's the premise of any convolutional neural network that we have. Okay, so so what is the basic intuition and basic idea behind convolutional neural network? So the basic idea is some of the high features can be much smaller than the whole image. For example, right now you can see probably there is a card in this image, right? And let's say the problem is a classification problem where we are interested in identifying cards in a given image. Then one way to identify for us is that we can identify some high level features. For example, the headlights of the car, right? They are typically present. So an image of a car will definitely have a headlight. Okay, and this is a smaller feature compared to the overall car. Similarly, tires are other features. The rear back mirrors are another features that are typically will be present in a given car. So can we identify those smaller features and use that as a basis to do recognition of objects inside a given image? So this is where what we are interested in, basically looking at these smaller features and basically using in a deep neural network framework through this transformation of with linear weighted and then non-linear transformation. We want to identify a given object in a frameworks, right? So that's where this car is headlight is located, and can we use this feature across multiple images, multiple different cars, and can we come up with a recognizer which uses this small scale feature is the main intuitive idea in the overall. So again, what we will be doing, if we can recognize these features, then we can basically compose in different layers different types of these feature detectors, which could be headlight detectors, which could be car tire detector, which could be rear view mirror detector. And if that is possible, then we will be able to compose a recognition system which basically sums up all of the small level features to identify the larger object in the overall image that we might have. Okay. So again, can we represent a small region with fewer number of parameters? And what we can do, as you will see, is we can take this thing and we can reduce the number of overall parameters that are needed in the network to learn object recognition. Okay. So again, if you have different images, and of cars, then the same feature, for example, the headlight, the car tires, or the rear view mirrors, they will appear in different location of the different images, right? So can we compress them, and can we create a system where we train some lot of the small detectors, and each detector can also move around in the image, so that we can identify even if those small features are located in any portion of that image or not. Okay, and that is what is the main intuition behind the main computational framework in the CNNs that we have. So right now you see there are two different cars that are here, right? And again, the headlight is here in this image, and we want to basically do the bottom right headlight detector by doing that. Similarly, in this image, we have a headlight right here, right? So we want to obviously detect that headlight, but you can see that the location of the headlight in the two different images are at different location. One is on the bottom right and one is in the middle. So can we create a system where we are probably scanning through the images, and we are going through the different location of the images to identify these specific features or not, is also the trademark of the CNNs and CNN computational framework that we have. Okay. So again, if we can identify that, then we can compress them to same number of parameters.